Okay, today we shall be talking about gas laws and their applications. And we shall be talking about, first of all, Boyle's law. What does Boyle's law state? Boyle's law states that the volume of a given mass of a gas is inversely proportional to its pressure. Volume of a given mass of a gas is inversely proportional to its pressure at constant temperature. So for Boyle's law, Boyles, that's the way it's spelled. For Boyle's law, temperature is kept constant. Now, for this law, I can rewrite this equation as V equal to K over P. That's introducing the constant K. And when I do that, the proportionality sign changes to equality. And when I cross multiply, this V is the same as V over 1. When I cross multiply, I'll have K times 1 equal to K equal to P times V equal to PV. This gives us P1 V1 equal to P2 V2 equal to P3 V3 equal to P4 V4, as the case may be. So this is Boyle's law, and we can use this formula to solve problems involving Boyle's law. So what Boyle's law is actually telling us is that when pressure increases, volume decrease. When pressure increase, volume decrease. Look at this illustration. Let's say this is a cylinder, and then this is also another one, and then there is a piston right here, and there is another piston right here. Let's assume we have the same amount of gas inside these two cylinders. Let's say the amount of gas we have here is equal to the amount of gas we have here. If you observe, there is enough space here for those gases, but here the space has been reduced. The space has been reduced, meaning that volume has been decreased here. So those gases here will not have enough space, so pressure will be high in here. But here, remember, the gases here are the same with the gases here, they are equal, none is greater. But here there is more space, so the volume here is great. Are you getting it now? There is large volume here, and because of this large volume, pressure is low. So when volume is high, pressure is low, and when pressure is low, volume is high. And in this case, when volume is low, pressure is high. So in this case, volume is low and pressure is high. But in this case, volume is high and pressure is low. So that's Boyle's law. Now quickly, we look at Charles' law. Now, Charles' law states that the volume of a given mass of gas is directly proportional to its absolute temperature in Kelvin at constant pressure. The volume of a given mass of a gas is directly proportional to its absolute temperature in Kelvin at constant pressure. So for Charles' law, pressure is kept what? Constant. Pressure is kept constant, meaning that pressure is not varied, pressure is not changed. So this implies that when temperature increases, volume increase. When temperature increase, volume increase. When temperature decrease, volume of the gas also what? Decreases. That's what this means. Now, working on this law, V, I introduce a constant, so proportionality changes to equal to, I have V equal to KT. When I make K the subject, I have K equal to V over T. It is from here that we have V1 over T1 equal to V2 over T2. So this is our Charles' law. This is our Charles' law. And don't forget, temperature must be in Kelvin. Temperature must be in Kelvin. So if you are given temperature in degrees Celsius, simply convert it to Kelvin. And how do you convert temperature from degrees Celsius to Kelvin? Simply add 273. When you add 273 to the degrees Celsius temperature, you get it in what? Kelvin. That's how to convert from degrees Celsius to Kelvin. Simply add 273 to the degrees Celsius temperature. The result will be in Kelvin. Is that understood? Now quickly, I want to show you the graph of Boyle's law and the graph of Charles' law. Okay, look at these two laws. Remember, Boyle's law states that the volume of a given mass of a gas is inversely proportional to its pressure. So this is a graph of inverse variation. So you can see as volume decrease, pressure what increase. This is volume on this axis and this is pressure on this axis. Now graph of Charles law looks like this from the origin pointing upwards, showing that as this increase, this also what increase. As volume increase, temperature also increase. So that's the graph of Charles law. Now next thing we're looking at is the general or the combined gas law. When I combine Boyle's law and Charles law, I get the general gas law. And here is the formula for the general gas law. Look at this. Remember, Boyle's law states that P1 V1 equal to P2 V2. Why Charles law states that V1 over T1 equal to V2 over T2. So when we combine these two, when we join these two, it means I have P1, I have V1. Are you seeing it? All over T1 equal to I have P2, I have V2 all over what? T2, which is the denominator. So this is the ideal gas equation. Or we can also use this PV equal to nRT. This is also the ideal gas equation. P is pressure, V is volume, N here is moles, N is moles, number of moles. R is the ideal gas constant. R is the ideal gas constant. It is a constant that will give you the value. The value of R is 8.31 joules per mole per Kelvin. Or if they are to give it in a different unit, they will give you the value to use. So they will always give you the value of R to use. And temperature is in Kelvin. Don't forget, we must always convert your temperature to Kelvin. And now we shall take a few questions on this. As I ask the question, we check which law is applicable, which law can be used to answer the question. Let's answer some questions on gas laws. This question reads, the pressure on 100 cm cube of oxygen gas at 35 degrees Celsius is 750 millimeters of mercury. What would be the volume of the gas if the pressure is increased to 100 millimeters of mercury without changing the temperature? It's a very simple question. Solution. The pressure on 100 cm cube of oxygen, meaning that the volume of oxygen is 100 cm cube. That's the first volume dimension, V1. At 35 degrees Celsius is 750 millimeter mercury. So pressure mentioned there is 750 millimeters of mercury. Now, what will be the volume? You see, they're asking about volume again. So this is the second volume, V2. What will be the volume? That was what we are looking for. If the gas pressure is increased to 1000 millimeters of mercury, so if pressure is increased to 1000 millimeters of mercury, what would be the pressure? Very simple. You can see P1, you can see V1, you can see P2, you can see V2. So we use P1 V1 equal to P2 V2. You remember this formula? So our P1 is 750, our V1 is 100, our P2 is 1000, our V2 is unknown. We are to find V2. So V2 is simply equal to 750 times 100 all divided by this 1000 we have here. So calculate it and give me the answer. I believe you have pressed your calculator now. That's 75. Therefore, V2 is equal to 75 cm cube. That's the new volume. If you observe, the initial volume is 100 cm cube at a pressure of 750 millimeters of mercury. Now, once the pressure is increased to 1000 millimeters of mercury, the volume is what? Reduced. Are you seeing it? That's to show you that volume is inversely proportional to what? Pressure. If volume increases, pressure decreases. If pressure increases, volume decreases. Now we take another question. Now we answer the next question. 30 cm cube of oxygen at 10 atmosphere pressure is placed in a 20 cm cube container. Calculate the new pressure if temperature is kept constant. Solution. Let's read. See, 30 cm cube of oxygen at a pressure of what? 10 atmosphere. So V1 is 30 cm cube and the pressure P1 is 10 atmospheres. 10 atmosphere pressure is placed in a 20 cm cube container. Remember, one thing about gases is that gases take up the volume of their container. If you put a gas in a 20 cm cube container, the gas occupies that entire volume. If you put a gas in a 30 cm cube container, the gas still occupies that entire volume. So a gas occupies the volume of its container. Now in this case, the gas was taken from the 30 cm cube container and placed in the 20 cm cube container. It means that the volume of the gas will change to what? 20 cm cube. That's the second volume. Calculate the new pressure, P2. We still use our formula P1 V1 equal to P2 V2. P1 10, V1 30, P2 unknown, V2 20. So P2 is equal to 10 times 30 all over 20. Press your calculator. That gives us 15. So the new pressure will be what? 15, not 15 millimeters of mercury, but 15 atmosphere, because the pressure we have is given in atmospheres, and that's the answer. Okay, hope you can see how simple it is. I don't think anything can make you fail a question on this. So we go again, another question. Okay, we answer the third question. At 25 degrees Celsius and 1 atmosphere, a gas occupies a volume of 1.50 dm cube. What volume will it occupy at 100 degrees Celsius and 1 atmosphere? It's a very simple question. At 25 degrees Celsius, that's T1, 25 degrees Celsius. 1 atmosphere, P1. A gas occupies a volume of what? 1.50. That's V1, 1.50 dm cube. Now, what volume will it occupy? So we are looking for V2 at 100 degrees Celsius and 1 atmosphere. Volume it will occupy at 100 degrees Celsius and 1 atmosphere. That's P2, 1 atmosphere. Now, if you observe in this case, we have both P, V, and T. So it means we are using the formula P1 V1 over T1 equal to P2 V2 all over what? T2. And if you can remember what I said earlier, I stated this clearly. Your temperature must be in Kelvin. If you are given temperature in degrees Celsius, you have to convert it to Kelvin. And how do you convert to Kelvin? By simply adding 273 to the degree Celsius temperature. Remember we said it earlier. Okay, let's convert 25 to Kelvin. When we convert 25 to Kelvin, that will be 298 Kelvin. You can see 100 degrees Celsius. When we convert 100 degrees Celsius to Kelvin, remember I said add what? 273. So 273 plus 100 will give us 373 Kelvin. So what we're using here is 373 Kelvin. Okay, now using our formula, P1 is 1, V1 is 1.50 over T1 is 298. P2 is 1 atmosphere, right? The same pressure V2 is 1 point, because V2 is unknown, and then T2 is 373 Kelvin. Now, there's something I would like you to observe. In this question, pressure was kept constant, meaning you can choose to use P1, that's a V1 over T1 equal to V2 over what? T2. Because pressure was kept constant. Remember Charles' law. In Charles' law, pressure was kept constant. How did I know pressure was kept constant? P1, 1 atmosphere, P2, 1 atmosphere. Look at it. At 20 degrees and 1 atmosphere, a gas occupies a volume of 1.50. What volume will it occupy at 100 degrees Celsius and 1 atmosphere? The same pressure. Are you getting the point? So if you use this formula, it matches just with this 1 1. So we have only this V1 divided by T1, V2 divided by T2. It's the same thing. Are you seeing it? Good. So let us do our calculation. We cross multiply. V2 multiplies 298, while 373 multiplies 1.50. Now V2 is equal to 373 times 1.50 all over 298. Use your calculator. So V2 is approximately 1.88 dm cube. Are you seeing it? Now let's compare. Temperature increased from 298 to 373. So volume increased from 1.5 to 1.88. Accurate. Okay, we answered this question. The number of moles of gas that occupies the cylinder of a bike 30 dm cube at 5 atmosphere and 97 degrees Celsius is dash. Let's answer this question. So the number of moles of a gas, they're asking about number of moles of gas that occupies is the cylinder of a bike. So V is 30 dm cube at 5 atmosphere. So P is 5 atmosphere and 97 degrees Celsius. So T is 97 degrees Celsius is dash, and they gave us the value of R 0.082 atmosphere dm cube per Kelvin per mole. So in this case, we're using the formula PV equal to nRT. But before we go further, remember I told you that if you have a degree Celsius temperature, you must convert it to Kelvin. So we have 97 degrees Celsius. We convert it to Kelvin, and that will give us 370 Kelvin. So this is 370 Kelvin. So we start. Our P is 5. Our V is 30. Our N is unknown. Our R is 0.082. And then our T is 370. Are you seeing how this formula works? So N is simply equal to 5 times 30 all over 0.082 times 370. Use your calculator. So that gives us 4.9 moles, which is approximately 5 moles. Therefore, N is equal to 5 moles approximately. Have you seen how we answer this question? It's very simple. Now, one final thing I want to show you is the graph of an ideal gas. This question is on ideal gas. The graph of an ideal gas looks like this. PV over RT here, and then You can have this. So the pressure, the graph of an ideal gas looks like this. It's a straight line graph moving horizontally. Are you seeing it? Moving horizontally. So this is the ideal gas. Whenever you see this kind of question, please, this is the graph of an ideal graph. I gave you the graph of Boyle's law, give you the graph of Charles' law. So this is the graph of an ideal gas.